All right, we will get started today. Uh, we're gonna we're gonna continue on with chapter 2, and before I do that, though, there's only I guess one announcement, or maybe perhaps better term, a warning for you, which is that recall that this is the week where we're gonna have the first of 2 chapter 2 assignments due. So it's gonna be due on Sunday, but if you wait until Sunday to do some or all of your attempts, which many of you are want to do. There's going to be 2 chapter 2 homework assignments available on Sunday, so make sure you do the correct one. Every semester there's about maybe 50 or so students that they frantically email me, I did the homework assignment last night, but now it's showing up as a 0, and it's because they did the wrong chapter 2 assignment that wasn't due until the following week. So there's going to be chapter 2A, chapter 2B. Just make sure you do the right one if you're going to wait until Sunday to do some or all of your attempts. Now, speaking of homework, what we're going to talk about this week in our Work Habit Wednesday is a little bit of statistics about the first homework assignment, just to see how we're doing and whether our effort level is appropriate. So the first thing, let's talk about, I guess, the good. So there's going to be the good and the bad. It's going to be sort of a mixed bag today. So the good is if we look at the average score. Now, I don't think average score tells us a whole lot in terms of the homework assignments, but if we look at last year, 2019, when I taught this exact same class in the spring semester, it was 10.37 out of 12. And then this year, you guys did significantly better at 10.78. Now, again, homework scores don't correlate that strongly with your final grade, but it does show that you were putting in mostly quality attempts, which is glad to see. Now, if we talk about the bad, though, or maybe the not as good, I don't want to be maybe too negative, but I'll just call it the bad for simplicity's sake. If we look at the number of attempts per student, so on average, how many times did each student do the assignment? Remember that would give you up to 4 attempts, and we only count your highest score, and your bonus score is determined by how many attempts you do. So really, there's no reason not to do all 4 attempts. But in 2019, there were about 3 on this first assignment. Now this number tends to drop off as the semester goes on, but there were 3.3 attempts. I'll just say 3.3. And then in 2020, this semester, there was 3.0, so a little bit lower. So on average, we did less attempts this semester than people last semester. As I said, my goal would be to have this number be 4, meaning that every one of you is doing all 4 attempts. Now, if you're one of the many people that did, keep it up. That's what you want. That's what I want to see. That's not all you have to do, but it's certainly a good start. So and then the other thing we can look at is for this semester, 301 students in this section, which is about 56%, did all 4 attempts. Okay, so we're looking at how many of you. So that means there's 44% that didn't. Now I suspect that the 44% that didn't do all 4 attempts and the 44% of the seats in this room that are empty are probably a fairly strong overlap. But nonetheless, I might be preaching to the choir a little bit. But nonetheless, there are a large number of you, 44%, that did not take advantage of all the opportunity to practice on the homework assignment. And if you also remember, this is purely coincidence, but maybe there's some significance to this. At the beginning of the semester, I said in the 5 years that I've taught this course, about 44% of students have gotten D's, F's, or withdrawn. And that's the same now as the number of students that didn't do all 4 homework attempts. So the point is, I don't want to be too mean or snarky about this, but if you're not doing all 4 homework attempts, which as I said is sort of the minimum level of effort you should be putting in, then I don't want to hear at the end of the semester complaints about this class was too hard, it's not fair that my exam was harder than my friends, I can't believe that 94% of the grade is exams, what are you guys thinking? I don't want to hear any of that if you're not doing the one thing you can control, which is your effort. So again, if you did all 4 attempts, I'm not yelling at you, good job, make sure you learn from them. But at the same time, if you're not doing that level of effort already in week 2 of the semester, then you're going to be setting yourself up for heaps of trouble later on when the exams come. All right, so that's the end of that. Let's get into the material. Yeah.
What was the goal of the average score for 2020 in overall? What was the goal?
The goal?
2020 for average. We need to get the average like close to 11.
Well, since the homework assignments are only 6% of your grade, we shouldn't be too concerned with the average score because it's not going to affect your final grade at all. And actually, one thing I've pointed out to some individual students is that if you get an 11 out of 12 on the homework versus a 12 out of 12, for your final grade, that's exactly the same because an 11 out of 12 will give you something 0.5, and a 12 out of 12 will just give you the number that we round up to anyway. So there's really no effective difference between 11 and 12 out of 12. the value of the homework assignment is in the learning gains that you get of knowing how to do the problems and knowing what to expect. So this number is going to drop throughout the semester because the material gets more difficult, and that's okay. I don't really worry about the number too much. It's good that it's high because that means a lot of you are putting in quality attempts and hopefully learning from those. But at the same time, I don't really worry about the score too much because it's not a big part of your final grade anyway, and it doesn't necessarily measure how much you learned from that assignment. Okay? Anything else? All right, so let's continue with what we're doing. So we ended up last time by defining quantum numbers. And so these quantum numbers were simple numerical parameters that are related to the wave equation, the wave function for an electron in an atom. And wave functions are very mathematically complicated, but they can sort of be decomposed or sort of thought of in part as these 4 quantum number parameters. We introduced 3 of them last time. There's one more we're going to talk about today. And basically, these simple numerical parameters allow you to define some things about the relative energy of the electron, the shape of the orbital, the shape of the region in space that the electron is occupying, and other important things where you don't have to, again, think about the whole mathematical parts of it. So we introduced some relationships. So there's these 3 quantum numbers that are all sort of related to each other in terms of what values they're allowed to have and what those values then mean for us. And so we're going to do a few example problems to start on the kinds of things that you'll want to be able to do on the next coming up homework assignments and the exams related to this. All right, so the first question here is how many subshells, and this is grammatically illiterate, but how many subshells have the principal quantum number n equals 3? I should get rid of that word r. So how many subshells have the principal quantum number n equals 3? So what we have to first remember is that what's the definition of a subshell? A subshell is defined as the first 2 quantum numbers together, n and l together. So anytime you pair up an n and an l, that defines a subshell. And then to think about how many subshells there are with n equals 3, so we're telling you the value of n for this situation. We want to know how many subshells included in there. So that's given to us. We have to remember the relationship. So L is going to be a value that starts at 0 and goes all the way up to n minus 1. So it can be any of those values, not just one or not just the maximum. But so L is going to be, in this case, 0, 1, or 2. The largest value of L is n equals 1. So basically, all 3 of these pairs are going to be subshells with n equals 3. 3, 0, 3, 1, and 3, 2 would be 3 allowed NL pairs where n equals 3. So that means there's going to be 3 subshells, okay? All right. And in general, so there is a bit of a shortcut here, although it's not one that's going to be terribly useful, but one that that can be helpful at times, is in general, for a subshell with principal quantum number n, so remember that, for a shell with principal quantum number n, so n defines the shell. In a given shell with principal quantum number n, there are n subshells. All right? So the n equals 1 shell has 1 subshell. The n equals 2 shell has 2 subshells. As we saw here, the n equals 3 shell has 3 subshells, in this case representing the different L values that are allowed, 0, 1, and 2. So that's a fairly simple relationship between the principal quantum number n and how many subshells there will be under that principal quantum number, okay? So that's one relationship involving quantum numbers. This next problem deals with a couple other relationships that we'll introduce. So then we want to know how many orbitals are in the third shell. And so for this, we have to remember what the definition of an orbital is. So we're going to talk today about sort of the more pictorial representation of orbitals, or how we think about them often in chemistry. But from the standpoint of quantum numbers, orbital is defined by 3 quantum numbers. So each orbital has 3 quantum numbers associated with it, and each unique set of 3 quantum numbers would be a different orbital in that atom. So it's going to be n, l, and m sub l. Those 3 together define an orbital. So one way to answer this question, we talked last time about the relationships between n, l, and m sub l. We dealt with the first 2 in the last problem, and then there's also m sub l being related to the quantum number l and how many values it can have. So one way to do this problem would be to just write out all allowed NL M sub L combinations for n equals 3. All right. Now there's a bit of a margin for error in that, obviously, because you have to make sure you don't miss any, and especially if n gets rather large, there's going to be a lot of combinations that you have to keep in mind. So that would be a very long and tedious way to do this, but it would work. You would basically figure out how many different combinations work for n equals 3, using, again, the relationships between the three quantum numbers and their allowed values. But there is some shortcuts that I think are going to be helpful to remember. So for a given n value, again, for a given shell number, we talked about last problem, the number of subshells is equal to n. The number of orbitals is also a simple relationship, n squared. All right. So in a subshell with the first quantum number being n, the number of orbitals in that shell would be n squared. Okay. Now for a given L value, this one we're not going to use in this problem, but we'll see it in the next one, so I'll just introduce it here. If we give you a subshell where we define n and L together, then the number of orbitals in that subshell is going to be 2L plus 1. Okay, so these are sort of the two key relationships for number of orbitals in a shell, number of orbitals in a subshell. For a shell, you only know the value of n, that defines a shell. For a subshell, you know a value of n and a value of L, which defines a single subshell. So in this question, we would have, we're in the third shell, n equals 3. We're only defining n, so we're going to use this first relationship here, and that means the number of orbitals for n equals 3 is 3 squared, which is 9. All right, so that would be the answer to this one, because in this problem, we're talking about just a shell number, n, and so we're going to use the n squared relationship to figure out how many orbitals there are. So you would have, if you had written out all possible combinations of n, L, and m sub L, which is a good exercise for you to do on your own if you wish, then you should have come up with 9 valid combinations, each of those 9 combinations representing one orbital, and that being why there's 9 orbitals in that shell. So you'd have, 3, 0, 0, you'd have 3, 1, minus 1, 3, 1, minus 2, 3, 1, minus 1, 3, 1, 0, 3, 1, 1, and so on. So there's 9 combinations. Again, it gets kind of tedious to do all that, but it certainly would work out. All right, and then this next problem deals with the other relationship. So we want to know, in this case, how many f orbitals are present in a given f sublevel. So two things about this. First of all, I'm telling you that it's a sublevel. So remember that a sublevel is going to be defined by an n and an L pair. Here we don't specify what n is, though, because we're just saying it's an f sublevel. And also, when you see the letters S, P, D, and F, you should, again, automatically think of the quantum number L, because that's what those letters represent. So what we have to remember for this is the different values of L that we can have being 0, 1, 2, 3, and so on, these being the 4 that we see most often. And these are going to correspond to letters that designate the subshell or the type of orbital that are in those subshells. So 0 would be S, 1 is P, 2 is D, 3 is F, S, P, D, F. So that means if we're in a F subshell or F sublevel, L equals 3. And it doesn't matter what the value of n is. L is always going to be 3 whenever we're in an F subshell. So if it's 4F, 5F, 6F, whatever F subshell we have, L is going to be equal to 3. And because we're defining a subshell with a given value of L, we're going to use the relationship that the number of orbitals in that subshell is equal to 2L plus 1. So anytime you know the value of L, either we give you both n and L together, or in this case we just specify what L is, you're going to use this relationship to figure out how many orbitals are in that sublevel that has that value of L. And so in this case, L equals 3, so this is going to be 2 times 3 plus 1, which is 7. And so the correct answer for this would be 7. All right, and that again doesn't matter which F subshell we're in, 4F, 5F, 6F, however high we go into the F subshells, there will be 7 orbitals in that subshell. Okay, so these relationships allow us to very quickly determine how many orbitals are in a subshell. And for some of them, as we'll show you later on today, hopefully, if we have enough time, you can use the periodic table to help you remember those numbers without having to always pull them out, especially for the ones that appear, these S, P, D, and F ones that we will see in regular ground state atoms. Okay, a couple other ones just to work through some more examples. So this one's going to ask us, what is the smallest principal quantum number that has d orbitals? All right, so principal quantum number being n, and then d defining the value of L. So here we're sort of working backwards through the relationships. So if we're talking about d orbitals, we have to again figure out which value of L that is. So we have L equals 0, 1, 2, 3, and so on. This is S, P, D, F. So d orbitals are going to be L equals 2. All right, so again, we want to learn those designations quickly because we don't typically use the numerical values of L. We always talk about them as S, P, D, or F in most common cases. All right, so L equals 2 for this one. We want to know what is the smallest principal quantum number N that has d orbitals. So here we have to work backwards through the relationships. So if we recall, the value of L is going to be equal to 0, 1, 2, and so on, all the way up to N minus 1. So if L equals 2, what's going to be our smallest value of N? You can go ahead and blurt it out. 3, right? So N has to be at least equal to 3 to give a value of 2. Okay, because if N is 2, the smallest value of L, the largest value of L will be 1. And so for you to have L equals 2, you need to have N at least equal to 3. So this is, again, knowing the relationships between the quantum numbers, in this case working backwards, giving you a value of L and looking for the value of N that could have that. So 3D is going to be the lowest D subshell. You won't have 1D or 2D. You'll have only 3D, 4D, 5D, and so on. Okay? Anything higher than that would give a D subshell. Okay, because remember that the value of L can be any number in this series. It's not just N minus 1, it's any of those numbers. But N equals 3 would be the smallest N value where you could have L equal to 2. Okay? Any questions on that or any of the concepts so far? Okay? Two other that are similar to each other. Here, again, dealing with how many orbitals there are. So when we're doing these questions, so I just gave you some relationships, number of orbitals being n squared for a given shell, 2L plus 1 for a given subshell. But if we give you a set of quantum numbers as a sort of a hint or warning in this problem, the first thing you need to make sure is that a valid set of quantum numbers. So don't just jump right to the equation. So we might be tempted in this one to say how many how many orbitals have quantum numbers NL equals 6, 6. Well, we're given a value of L, so it's going to be 2L plus 1. 2 times 6 plus 1 is 13. Put it in Blackboard and move on, and then get dismayed when you get the question wrong. And because what you have to make sure you do is every time we give you a set of quantum numbers, make sure they're actually a valid set of quantum numbers. So if we look at this set here, n equals 6, that means the allowed values of L, again, are going to be 0 up to n minus 1. So the possible values of L for n equals 6 are going to be 0, 1, 2, 3, 4, 5. And so what we see here is that 6, which is the value of L that I gave you here, 6 is not an allowed value of L. So that means there's going to be a big fat 0 orbitals that have these quantum numbers, because if this is an invalid set of quantum numbers, in other words, 6 and 6 cannot be together, n cannot be 6 and L cannot also be 6 at the same time. If that's the case, that means there are 0 orbitals that have those quantum numbers. That's a disallowed case. So whenever you're doing problems like this, make sure that, if we're asking how many orbitals are there, how many subshells are there, make sure that we're starting with sort of a valid situation. So this cannot work for anything because the value of L is not one that we can have. Okay? Is that, you might call that a trick question, but it does, again, make you think about the rules involving the relationships. Now, if we go to this one here, very similar problem, but this time I gave you quantum numbers NL is 7, 5. And if we do the quick check, n equals 7, L can be anything of 0, 1, 2, 3, 4, 5, up to 6, n equals 1 being the largest value. So the pair 7, 5 works just fine. Remember, it can be any of these L values. So this is an okay subshell designation, n equals 7, L equals 5. And so if we want to find the number of orbitals here, remember that if we give you n and L together, or if we specify L in any sense, you have to use the value of L to determine how many orbitals there will be. So if we know the value of L, in this case we do, it's again going to be just 2L plus 1. So there's two simple relationships for finding number of orbitals in a shell or a subshell. Here we're going to use the one for a subshell since that's what we're designating. And it's just going to be 2 times the value of L, which is 5 plus 1 equals 11. Okay? So there would be a total of 49 orbitals with n equals 7, 7 squared being 49. 11 of those would have L equals 5. So there's, that's the difference again between shell and subshell. Shell would include all of the orbitals that have n equals 7. The 7, 5 subshell, which I guess would be 7H, if you're doing by letters, would have 11 orbitals in it. All right?
Why'd you include the 6 for the L?
Well, this is one of the possible values of L. So basically the first thing I checked was, can 5 actually be a value of L for n equals 7? And for n equals 7, L could be any of these 7 values, including 6. Here we're specifying that it's 5, but it's an allowed value. That's what we want to check first. Whereas in the previous problem, I gave you a value of L that wasn't even valid, so that's why the answer was 0. Okay? Anything else? Yeah. L cannot go greater than n minus 1, yes. So it cannot be equal to n or greater than n. All right, other questions? Yeah. That's the number of orbitals in a shell for given n value, yes. In this case, though, we're designating n and L together, so you want to use the L value, yeah.
How did you got the L on 5?
Because I'm telling you here in the problem that the quantum numbers we're considering are 7 and 5. It's right here. So you know, as I said, the L value could be any of these. We're specifying here that we're talking about the L equals 5 subshell, so that's the value of L we want to plug into this equation down here.
It's not the 5 on the y-axis?
It's not the y-axis, it's the L value that we're specifying in the problem. So it's n and L equals 7, 5. So here when you...
I thought it was a 1. You should have put like cursive L on it.
Is this a cursive L or not?
Yeah, like that.
That's what I did. I'm confused what you're...
No, talking about cursive L when you type on my computer, it makes it confused like L or 1.
Oh, yeah, that's too much effort in Microsoft Office, so I didn't do that. Sorry about that. I understand what you're saying now, but yeah, maybe I'll fix that in the future, maybe not, but sorry for the confusion. All right, any other questions? Okay, sorry. All right, let's move on then. After that auspicious ending. Okay, so we're going to talk now about the shapes of atomic orbitals, and you know, knowing the relationships between quantum numbers is important. We're gonna test you on that and things. But what's, I think, from a chemistry standpoint, even more important is knowing some things about what the quantum numbers mean, and specifically what they mean about the shapes of the orbitals. So as we said, the way we often think about orbitals, an orbital is often synonymous with a wave function, which, as we've talked about, is a complicated mathematical equation for the electron as a standing wave in an atom. Very abstract concept. But the way that we think about them in chemistry is, remember that the wave function is related to the probability of finding an electron at a certain spot around the nucleus. And then if we square the wave function, that's again related to probability more specifically. And then we can define an orbital as sort of a region in space where the electron is most likely to be found. And that region in space is going to have some characteristic shape associated with it. And as we'll see, the shape is going to be determined principally by the quantum number L. So the different L values that we have, 0, 1, 2, 3, and so on, are going to define the shapes of the orbitals that have that L value, okay? And so that's how we also think about it, because as we will circle back to later on in probably chapter 4, the shapes of the orbitals are very important for determining how the atoms can bond to each other to make molecules, what shapes those molecules can be, and so on. So all this stuff will sort of stick around for a while, but we need to understand the shapes of the orbitals and how that relates to these quantum numbers that we've just defined. So before we get into that, let's define some key terms first. So a node is a region where the electron has 0 probability of existing, okay? Another way of thinking about it is it's a region where the wave function goes to 0. So remember that wave function is a mathematical function in terms of x, y, and z, and for certain values of x, y, and z, that wave function could have a value of 0. And it also means then that at those positions, the electron has 0 probability of existing, right? So it's a place where, rigorously speaking, mathematically speaking, the electron cannot be there, okay? And as we'll see, there's 2 types of nodes here, radial node and nodal plane. So a radial node is a certain radius. So some distance from the nucleus, r. So it's, again, relative to the nucleus is sort of our origin point here. And it's a certain radius where the probability of finding an electron is 0. All right. Radial nodes are not terribly important from a chemistry standpoint, but they do define some important things we'll talk about later in terms of the relative energies of orbitals. But to determine how many radial nodes there are is fairly simple. It's another, I guess, equation, if you want to call it that, that is in terms of n and L. And so the number of radial nodes is equal to n minus L minus 1. All right, so cursive L and number 1, to be clear, which is more clear when I write it than when I type it, which is rare, that my writing is more easily interpretable than my typing. But that's going to be the number of radial nodes, n minus L minus 1. And so that's what we have for radial nodes. And it's, again, a certain distance from the nucleus where the electron can exist. And then we have nodal planes, which a little bit harder to visualize, I suppose, but it's going to be a two-dimensional plane where the electron, sometimes these are called nodal surfaces because they don't necessarily have to be flat, I suppose, and a plane implies that they're flat, but it's basically a two-dimensional surface where the electron has no probability of existing. Now, you don't have to be so concerned with, in the different types of orbitals, identifying and visualizing where exactly the nodal planes are, but the key point is that the number of nodal planes dictates the shape of the orbital. It's really the most important thing for dictating the overall shape. And it's actually very simple to know how many of those there are because it's just given by L. All right, so the number of nodal planes does not depend on the value of n at all. It just depends on L, and it's exactly equal to L, okay? All right, so that's going to be the two types of nodes that we're going to deal with and that are going to help us then talk about, to some extent, the probability distributions of orbitals, which we kind of touched on a little bit last time, but more importantly, the sort of gross overall shape of them. So if we go to the first type of orbitals, which are s orbitals, and so remember that these letters designate the value of L, so s means L equals 0. The shapes of these are very simple, so I'm not even going to really attempt to draw them. They're just spheres, okay? We kind of talked about that for the ground state hydrogen atom. As it turns out, and we'll talk about it in more detail a little bit later on, the ground state of hydrogen has its electron in an s orbital, specifically a 1s orbital. So we said the ground state of hydrogen has a spherical electron density that's defined by the wave function, and that's because that corresponds to an s orbital. So any s orbital is going to have a spherical shape. And there's going to be no nodal planes because L equals 0, the number of nodal planes is 0. And so that means every s orbital is spherical shape, but the difference is going to be in how many radial nodes they have. So if we look at a 1s orbital, so as you'll recall, the number of radial nodes is n minus L minus 1. So n is 1, L equals 0, minus 1 is 0, okay? So for 1s orbital, there are 0 radial nodes, and we're going to have that same probability distribution that I showed you before. So the y-axis here is 4 pi r squared psi squared, if it's not big enough for you to see, and the x-axis is radius. So basically, as we go from close to the radius to far away from the radius, we're going to have a relatively simple distribution that looks like this. As we talked about last time, there's a peak, a maximum radius, a maximum probability where the electron can exist, and it tails off to smaller and smaller numbers, but never quite gets to 0. And so for a 1s orbital, you have a simple probability distribution like this and 0 radial nodes. Typically, these radial probability densities are not, we mostly think about them for s orbitals, which are spherical and then thus the same in all directions, but other orbitals would have these too. If we go to a 2s orbital, so it's still an s orbital, still L equals 0, so still spherical in shape. In this case, though, n equals 2 and L equals 0 still. And that means n minus L minus 1, 2 minus 0 minus 1 is going to give us 1 radial node. So the difference between these s orbitals, 1s, 2s, 3s, and so on, is the number of radial nodes that they would have. And what that then does for the probability distribution is it gives it a more complex appearance, where now we have sort of a small peak in probability close to the nucleus. It goes to 0. That's your radial node, where the place where the probability is 0, and then you have another peak farther away. All right, so the average radius, or the most probable radius, is further away. So as the n value gets larger, the most likely radius for that electron gets further and further away from the nucleus. That's always going to be true, but we do have a little region of probability that's also close to the nucleus. In this spot here, where the probability goes to 0, let me do it in a different color so it's easier to see. This spot here where it goes to 0, that would be our radial node. All right, and so again, that's the place where the electron has 0 probability of existing. Now, one of the big mysteries in life that people have debated for the last 100 years is, well, if you have a region over here close to the nucleus that has non-zero probability, another region over here that has non-zero probability, how do you get from here to here while going through a region that has 0 probability? How is that even possible, right? You have to go through this radius to get from here to here, but this has 0 probability of the electron being there, so how does that happen? Now, that's a property, we're not going to talk about it, but that's a property called tunneling. It's, again, think of it more as, the electron as being a wave, a standing wave equation, not as like a particle moving through space. And basically, it's one of those sort of mind-bending things about quantum mechanics that we're not going to talk about, but is something that people still debate to these days. Now, in terms of what a 2s orbital would look like, what you would basically have then is, see how I, so it would be spherical in shape, sort of spherical in shape. Oh God. All right, we're back. So it's going to be spherical in shape, but then it's going to have a radial node, basically a place where the electron can exist, but it's still going to look like a sphere. I'll draw that again in maybe a different color. That's sort of the radial node, and then you're going to have equal sort of spherical electron density around the nucleus, but one place where the electron can exist. So a little bit hard to draw in 3 dimensions, but basically think of it as a sphere inside of a sphere. There's basically one radius, one value of the radius where the electron can't be, and it's kind of like 2 spheres inside of each other where the electron could be and has a probability of existing. If we go to 3s, where n equals 3, L equals 0, we now have 2 radial nodes as you follow the pattern. And so the probability density is going to look even more complex because it's going to have 2 places where the probability goes to 0. So it's going to look something like this. And again, a most probable radius that's even further away. But now we have 2 places here and here where we're going to have 2 radial nodes. So those are the 2 places where the probability density goes to 0 as we go away from the nucleus. All right, so those are sort of some things about the shapes of the atomic orbitals. These are the only ones we're going to really look at these probability densities in detail. For the rest, we're just going to mainly draw them. Yeah?
So are the peaks of each
Yeah?
Yeah, are they attributable to higher and higher?
Yeah, so basically the probability as you get further away from the nucleus for each of these peaks is larger. So remember, the y-axis is how likely it is to find it there. So there's a small probability, and I don't know if I drew it perfectly to scale, to be honest, but there's a small probability of finding it close to the nucleus, but the most probable radius is going to be the peak that occurs furthest away. And as I tried to indicate here, those maximum peaks get to larger and larger radiuses as you go from 1s to 2s to 3s. So one thing that the value of n determines is how big the orbital is, if you want to think about it that way, which is, again, the most probable value of the radius being further and further away as the value of n gets larger and larger. But there is going to be some small probability of being close to the nucleus as well when you have these radial nodes. All right, so any other questions before I move on? Yeah? Well, it increases to a point and then decreases again. And so that relates to what we talked about last time, which is that this radial probability density is the product of 4 pi r squared times psi squared. So the probability density psi squared will actually increase as you go to smaller and smaller radius, but then r squared is going to decrease as you go to smaller and smaller radius. So you have basically 2 opposing functions, and the product of those 2 results in peaks at certain positions. And when you look at the wave function as a function of these quantum numbers n, l, and m sub l, the value of n is essentially related to the radius of the wave function. You want to think about the square of the wave function being a sphere as it is for an s orbital. As n gets larger, the radius of that sphere gets larger and larger, and that's why these values get further and further away. It's sort of a simplified way of thinking about it, but that's kind of what it relates to. Yeah?
What is the significance on knowing how many radial, I guess, each
how many radial nodes there are?
Yes.
Yeah, so from the significance is from helping you understand the basics of quantum mechanics, I suppose. It is a very dumb answer, but as we'll see later on, with these probability densities and the shapes help us predict is sort of the relative energy of orbitals. So if we're considering, as we'll see later on, two orbitals that have n equals 3, let's say a 3s and a 3p, which one's lower in energy? It turns out that this small probability of the electron getting close to the nucleus has a big impact on the energy of that orbital. And so understanding the differences between these probability densities allows us to predict whether the s or the p orbital will be lower in energy, for example. And we'll get to that probably later today or next time. Okay? Anything else? All right, so let's go on to the next type, which are p orbitals. There's going to be only 3 types of orbitals that we expect you to know the shapes of, so they don't get too complicated. So a couple things about p orbitals. First of all, that means if we're in a p orbital, L equals 1, we're going to do 2p specifically, but any p orbital would have the same basic shape. If L equals 1, that means we have one nodal plane, because n minus L, for 2p anyway, n minus L minus 1 is going to be 2 minus 1 minus 1. So that's 0 radial nodes, and then we're going to have one nodal plane because L equals 1. Sorry, I said that wrong. One nodal plane, 0 radial nodes. And so the other thing that we have is because L equals 1, we have 3 different m sub L values, which is going to be -1 to +1. And so because we have 3 different m sub L values, that means anytime we have p orbitals, L equals 1, we have 3 individual orbitals. So in s orbitals, m sub L equals 0, there's only one s orbital at every energy level, 1s, 2s, 3s, and so on. But for a set of p orbitals, we're going to have 3 different orbitals because we have 3 different m sub L values that are allowed. So we'd have, for 2p orbitals, 2 1 minus 1, 2 1 0, 2 1 1. We'd have 3 individual p orbitals. Now there's not a one-to-one correlation here, but as we'll see, what these 3 different m sub L values designate are 3 different orientations of those p orbitals. So the p orbitals are all the same shape, but they're just oriented differently, as we'll draw here in a second. We can also talk about the radial probability density for a 2p orbital, although I said we're not going to go into much detail with other orbitals besides s on this. But it's going to look qualitatively similar to the 1s, because if we have n equals 2, L equals 1, we're going to have 0 radial nodes. And that means we'll just have a simple probability density that looks, in terms of the radial probability, similar to an s orbital. Some maximum value at some radius, and then it decreases as we go to larger values. So not a huge difference there in terms of the radial probability density, but what is different is sort of the angular probability density. So these wave functions are, we said they can be defined in terms of x, y, and z, but they can also be defined in, if you're familiar with polar coordinates, in terms of a distance r and an angle part, which is dependent on a couple different angles relative to the origin. And the angular part for p orbitals is way different than the s orbitals, and that's why they have completely different shapes. So the shape of a p orbital is going to look sort of like a figure 8, or some call it a dumbbell shape. And they're going to be oriented along the 3 different Cartesian axes. So we're going to have px, py, and pz. So to designate the 3 different p orbitals that we have at any given p subshell, they're going to be along the x, y, and z axes. And so those names tell you exactly how it's oriented. It's going to be a figure 8 along each of the axes. So px is going to look something like this. Now, one thing that your book does not do, but I think it's helpful to start introducing it now, is that the other thing about p orbitals, so for the s orbital, it's just a spherical shape, and one thing that means mathematically is that the wave function is positive in all directions. But for a p orbital, you actually have, as you cross through this origin where you have sort of the intersection point between the 2 lobes of the p orbital, you have a change in sign for the wave function. So the way that these are often drawn is with one of the lobes shaded a different color. I'll just do a shaded and unshaded to not have to use different colors. But that's sort of one way to designate a p orbital, where you have 2 different lobes, and the different colors indicate that they have, the wave function has different signs in the 2 directions. There's no real convention on whether colored means positive or unshaded means negative. There's no real convention there, but it just means that as you cross through the origin point, the sign of the wave function changes. The probability is symmetric, so the probability on each side is the same because the probability is the square of the wave function, but the actual sign of the wave function itself goes from positive to negative as you cross the origin. That's not so important for us right now, which is why your book doesn't even introduce this point, But when we start talking about bonding later on in chapter 3 and chapter 4, the signs of the wave functions can be important to consider for bonding. Because remember, they are mathematical functions, so they can be positive or negative. And in a p orbital, you have one region that's positive, one region that's negative. And that's how I'm going to draw them to indicate that, okay? So if we go to py, it's the same shape, but now it's along the y-axis, as the name suggests. So it's just going to be a figure 8 or dumbbell shape along y, with one of those, again, being a different sign than the other. So I'll indicate it like that. And then pz is along the z-axis, and again, exact same shape, just oriented in the z direction. Okay? Now, obviously, we can't ask you to draw things in Blackboard, but you will have to look at pictures of orbitals potentially and identify which ones they are. So for the p orbitals, all of them are sort of this basic figure 8 or dumbbell shape, and the direction of the p orbital is just x, y, or z, so fairly simple. The other thing we can define, I don't think we'll necessarily directly ask you about this, but we might, but it's helpful to imagine, is, as we said, all of these orbitals are going to have one nodal plane. The value of L tells you how many nodal planes there are, so these all have one because they're all L equals 1 orbitals. And the nodal plane for a p orbital is just the plane that's perpendicular to the direction of the orbital. So if you recall your geometry classes back in high school, if you have something along the x-axis, the plane that's perpendicular to x is going to be the other two axes, y, z. So remember, every plane is defined by 2 coordinates, so it's going to have a yz nodal plane, okay? So an orbital that's along x, the yz plane, which I'll sort of outline here, is going to be the plane that's perpendicular to that, and that would be the nodal plane for that orbital. And then for py, the nodal plane is going to be the other 2 coordinates are going to define that nodal plane, so it's going to be x and z. So the xz plane would be the nodal plane for a py orbital, and then for pz, x and y, that plane would be the nodal plane. All right. So for p orbitals, defining the nodal plane is very simple because the orbitals are just defined with a single coordinate x, y, or z, and then the plane that's the nodal plane is going to be the plane that's perpendicular to that in the other 2 directions. So it's again fairly simple geometrically. All right, so those are the p orbital shapes, sort of intermediate in terms of their complication. The most complex we'll get to are the d orbitals, and there are and that's what we're going to sort of end with. So if we have the d orbitals, we're going to have, if we're doing 3D specifically here, n equals 3, L equals 2 for the 3D orbitals. So that means we're going to have 0 radial nodes again for 3D specifically. And then for any d orbital, whether it's 3D, 4D, or higher, L equals 2, which means we're going to have 2 nodal planes. Okay, so if we draw the radial probability density for a 3D orbital, again, the scale would be a little bit different, but it's going to look very similar to 1s and 2p because it has 0 radial nodes, so it's just going to have some maximum probability radius and some distribution as you go in both directions. But what we're really interested in talking about are the shapes of the d orbitals, which, as I said, are a little bit more complicated, a little bit harder for me to draw, but I think I've done it enough times that I won't fail miserably. And we have pictures on the next slide that are from your book that might be a little bit clearer in some respects. Okay, so there are 5 different d orbitals because if L equals 2, there's going to be 2L plus 1, which is 5 different orbitals. Or alternatively, m sub L is going to be -2, -1, 0, 1, and 2. 5 different m sub L values means that there's 5 different d orbitals, all oriented differently in space in different directions. All right, now the d orbital names are also indicative of their relative orientation. So the first one that we'll start with is dxy. So as the name suggests, the orbital is oriented in the xy plane. And so if we highlight the x and y axes, that's going to be the plane that this orbital is oriented in. And what it looks like, 4 of the 5 d orbitals all look like 4-leaf clovers. So they're going to have 4 lobes. And in the xy orbital, those lobes are going to be between the x and y axes. So you're going to have one lobe that points like this, one lobe that points like that, and then they're kind of the same shape but sort of into the page that are going to go between all the x and y axes. So the 4 quadrants of the xy plane all have one of these d orbital lobes in that. And the phases of those lobes are going to alternate between positive and negative. So as we said, the wave function can have signs associated with it. And anytime you cross through a nodal plane, you have to change the sign of the orbital. So the result is that for d orbitals, you have alternating plus and minus directions, plus and minus signs as you go around the orbital. So that's dxy. And then the other one that's in the xy plane is called dx squared minus y squared, okay? So again, the two letters are x and y, so that tells us it's in the xy plane. The only difference in this case is that the lobes of the x squared minus y squared, instead of being between the x and y axes, they are directly on the x and y axes. So this is again in the xy plane, so we're going to highlight those axes as being the sort of primary direction of this orbital. They are three-dimensional, so they do have amplitude in the z direction, but their basic orientation is in x and y direction. And so you're going to have, in this case though, for x squared minus y squared, the four lobes are going to be right along the x and y axes. Okay, so they're in the plane of the xy, but along the axes directly. And so the only difference between xy and x squared minus y squared is that they're just rotated 45 degrees relative to each other. This one being in between the axes, this one being right on the axes, but they're just 45 degrees rotated, same shape, just different orientation slightly. Okay. The other two d orbitals that are four-leaf clover shaped are just going to be in the other plane. So we have xy, so we're going to have the other two planes being xz and yz. The name again indicating the direction of that the orbitals are sort of pointing, the lobes of the orbital are pointing. So if we have dxz, we're going to have these two are going to be our axes of orientation, and we're going to have lobes that fall in those four quadrants between the axes. All right, so this one will kind of be rotated a little bit from the plane of the page, but hard to draw exactly right. But it's going to be four lobes that are in between the x and z axes. Then if we go to the yz orbital, that's going to be the one that's easiest to draw in this well, maybe actually not easy. Sorry, I did the coordinates weird here. But for yz, it's going to be the y and z axes, and it's going to be lobes that are in between the y and z directions. Okay. So these first four orbitals that I drew all have the same shape. They're just oriented differently in space. And the x, y, xz, and yz are just rotated 90 degrees from each other in different directions. Okay, so they all look the same. They just have different orientations. And so, if we give you pictures on the exam, we'll give you clear enough pictures that it's obvious to tell what the directions are, in case my own drawings are not super obvious. The last d orbital that we have is sort of the oddball. It's called dz squared. And so as the name suggests, its principal orientation is only along the z-axis. And what this one looks like is, it at first kind of looks like a p orbital. It's a dumbbell shape or figure 8 shape. But in this case, the two lobes are the same sign. They're not opposite signs. And it also has what's called a torus, or more colloquially speaking, a donut that goes around the orbital like this in the xy plane. So basically think of it as a figure 8 with an inner tube around its waist, if you want to think about it that way. Yeah. Yeah, it's opposite sign of the two primary lobes. So yeah, they are indicated correctly with the signs being one positive, one negative. Yeah, opposite in signs for the two. Yes. So xz and yz are just in the different planes. So xz. Yeah, so basically the way that I've drawn it, xz would be sort of coming, well, I kind of drew them at a weird angle, but basically xz would be like this, in this direction, and then yz would be 90 degrees to that in that direction. So both sort of coming out of the board towards you. There's pictures on the next page that maybe are a little bit more helpful, but they're just different orientations. One is facing one way, one is facing 90 degrees relative to that. If I had redefined the coordinate system so that, let's say, one of the planes was actually in the plane of the board, if you had dxz was flat in the board like this, dyz would be turned 90 degrees relative to that and be coming out straight towards you. So they're just different with respect to their rotation about the origin and just 90 degrees apart from each other. So you have to be able to picture things in 3D, and you have to be able to draw things in 3D, which I clearly can't do very well. But at the same time, that's really all the difference is how they're oriented. And then dz squared is sort of the oddball d orbital because it has a totally different shape. In this case, it doesn't really have nodal planes. It has what are called nodal cones, which would be cones that sort of radiate out from the origin in each direction that define the nodes. That's more complicated too from that standpoint, but it's just a dumbbell with an inner tube around it is sort of the way to think about it in simpler terms, okay? That's as high as we're going to go. We're not going to go to the f orbitals. I wouldn't even be able to attempt to draw those, and they're very complicated. There's 7 of them, so we're going to stop there. Here's a reproduction. Don't answer the question if they do or do not suck. I don't need to know that. But then this is, again, some better pictures, perhaps. They're in your textbook, I believe, so you can see them there as well. These 5 being the 5 individual d orbitals. And so you can imagine those lobes that I drew as sort of balloons, if you will, like sort of, orbital shaped balloons that protrude in each direction. This one does not show the different phases of the orbitals. As I said, your book doesn't do that, but the shapes are maybe more clear than what I drew, okay? So as I said, all you're gonna really have to be able to do for that, for now, is just be able to, identify the pictures. If we give you a picture of an orbital, tell us what it is. We'll see later on how the shapes of the orbitals, especially the s and p, can be important for determining how atoms bond to each other when we make molecules, but that's coming later. All right, any questions on that topic? All right, so just a couple of sample problems on that topic to wrap up this section. So which of the following orbital designations is incorrect? So a very similar problem to what we had before, this time including the letters as well as the quantum numbers. So the first thing, again, to look at is whether the value of n and L are compatible with each other. So n can be 1, 2, 3, 4, and so on. So all these values of n are certainly possible. If n equals 2, as we have for choice A, L is going to be equal to 0 or 1. So n equals 2, L equals 0 is a valid combination. And remember that the value of L tells us which letter we're talking about, SPDF. All right, so n equals 2, L equals 0 is an okay combination. If it's L equals 0, that means it's S, so that should be correct 2S, so this one's okay. If we go to choice B here, where n equals 3, allowed values of L are going to be 0, 1, and 2. So n equals 3, L equals 1 is an allowed combination, but then it's going to be, is it 3p? L equals 1 tells us it's a p orbital, so this one's okay as well. For choice C, n equals 4, the allowed values of L are going to be 0, 1, 2, and 3. So the combination n equals 4, L equals 2 is an allowed combination. L equals 2, does that correspond to a d orbital? It does, so that one's correct as well. So that means the last one is probably the one that's incorrect. Let's check if that's actually true. If n equals 3, L can be 0, 1, or 2, as we saw up above. L cannot be 3. Okay, so that's an invalid value of L, so this is an incorrect designation. Okay, so L equals 3 does indicate an f orbital, but there's no such thing as a 3f orbital, because if n equals 3, L cannot also be 3, similar to a problem we saw earlier today. All right, and then again, the types of questions we might ask you about the shapes of orbitals that we just went through would be something like this. We give you the picture of an orbital. My hand drawing is not up to snuff, but I can use computer programs to maybe draw them better. This is one of them. In this case, I did orient the orbital directly in the plane of the page, so that makes it even a little bit easier to interpret. And what we want to look at is which orbital is pictured here. So again, the first thing to think about is what's sort of the basic growth shape of the orbital. It's a 4-leaf clover, or an orbital that has 4 lobes, and that automatically tells us that it's a d orbital. Okay. So the first thing you want to think about when looking at a picture of an orbital is it S, P, or D? Is it spherical for S, figure 8 for P, 4-leaf clover for D, or there's one weird d orbital, but anyway, this is clearly a d orbital, so we can get rid of choice A. Now we just have to figure out the orientation of it. So pretty clearly, these lobes are oriented along the xy direction, so it's not dz squared, which is the sort of the last one we drew on the previous one along the z axis. So it's one of these two. These are the two that are probably the hardest to remember and distinguish from each other, but the one where the lobes are directly on the axes as we have here is going to be x squared minus y squared. So dxy would be in the same plane, but it would be rotated 45 degrees and sort of have this orientation to it, okay? So it'd be in between the axes as opposed to directly on the axes as I'm showing here. All right, so that's, again, just the types of things we want you to do for orbital shapes for now, nothing too in-depth or complicated, just knowing the quantum numbers and what they mean. All right, so we're going to move on now from orbitals and start talking about individual electrons. So when we have an atom that has one or more electrons in it, what we're going to be able to do is we're going to define a set of quantum numbers for each individual electron in the atom. Now those first three quantum numbers that we've already been talking about a lot, N, L, and M sub L, those are going to tell you which orbital the electron is in. But there is a fourth quantum number that's specifically for the electron itself, independent of the orbital, and that's called the spin quantum number. Okay? And it's abbreviated as M sub S, so we have NL, M sub L, M sub S, as we'll review here in a second. And it only has two possible values, plus 1/2 and minus 1/2. Okay, so it's just one of those two values. It's the only one that's not an integer, but it only has those two values. It doesn't depend on any of the other quantum numbers, NL and M sub L. It's just plus 1/2 or minus 1/2. Okay, and sort of the way we refer to that in words is we don't usually say plus 1/2, minus 1/2. We usually say spin up, spin down. Okay. So if M sub S is plus 1/2, that's a spin up situation. If M sub S is minus 1/2, it's spin down. And that's how we sort of call it. And as we'll see later, we often just abbreviate those spins with arrows pointing up or pointing down. So it's pretty simple. Only two possible values. Now, what does it mean? It's a property of an electron itself. So an electron, whether or not it's in an orbital, we're going to talk about electrons in orbitals because we're chemists, but if you had just a free electron, it would also have an M sub S value. So it's a property of the electron itself. It's not determined by the orbital that the electron is in. And what it basically refers to is the direction of its magnetic field. So anytime you have a charged particle like an electron, it's going to have a magnetic field associated with it. And the direction of the magnetic field for the electron can be in the positive or negative direction, which designates an M sub S value of plus 1/2 or minus 1/2. So that's physically what it means. It turns out, as we'll see in a little bit, the M sub S value has no bearing on the energy of the electron unless you're in a magnetic field, again, which we're not usually in a magnetic field. So it really has no bearing on the energy. So whether the electron is spin up or spin down in an orbital has exactly the same energy. So there's no difference between those two in terms of determining the energy of the electron in the orbital. Okay? So that means what we're left with is a set of four quantum numbers for each electron in an atom, NL, M sub L, and M sub S. These first three together, as we've already talked about a lot, tell us what orbital the electron is in. And then the last one, M sub S, is a property of the electron itself, its magnetic field being pointed up or pointed down. So those set of four quantum numbers are going to allow us to define each electron in an atom. Everything we want to know about that electron can be given by those four quantum numbers, which orbital it's in and whether its spin is up or down. So when we're defining the four quantum numbers for an electron in an atom, one thing we have to follow is what's called the Pauli exclusion principle. So this guy was, again, one of those scientists who was particularly unhappy about his fame in history, but he is a very important scientist nonetheless, Pauli. And he came up with this exclusion principle, which is that no two electrons in an atom can have the same set of quantum numbers. So in other words, each electron in the atom, however many electrons you have for that atom, is going to have a unique set of four quantum numbers. No two can be identical to each other in terms of having all four of the same quantum numbers. Okay? Now that again refers to the complete set of quantum numbers. That doesn't mean that none of them can be the same, but you cannot have the same set of four quantum numbers for two different electrons. Okay? So that's kind of almost like you can think of it as like a barcode for each electron. It's going to be a unique designator for each electron. Each set of quantum numbers is unique for one electron in the atom, and no more than one. So there are some implications for this. So as we recall, the first three quantum numbers, NL and M sub L, define an orbital. And then the last quantum number, the fourth one, M sub S, can only have two values, plus and minus 1/2. And so what this tells us then is that if we have electrons in an orbital where the first three quantum numbers are the same, NL and M sub L, there's only two possibilities for the fourth quantum number. It's either 1/2 or minus 1/2. That means there's only two sets of quantum numbers for that specific orbital. Or a simpler way of saying this is that you have a maximum of 2 electrons per orbital. Okay, so when we're deciding, how many electrons does each orbital have in an atom, typically for the ground state of the atom, as we'll learn how to do, there's going to be no more than 2 electrons per orbital. It's Otherwise, you have to violate Pauli exclusion principle and have 2 electrons that have the same quantum numbers. Okay, so the last quantum number has to be either up or down. That defines basically 2 ways of putting that electron into the orbital, meaning only 2 electrons can be there. And what it also means is that if we put 2 electrons in an orbital, now each orbital is not necessarily going to have 2 electrons. It can have at most 2 electrons, but in the case where the orbital does have 2 electrons, the spins are opposite, or what we call paired. So when we say the spins are paired, that means they're opposite, meaning one of the electrons is plus 1/2, the other electron is minus 1/2. Or another way of saying this rule is that it is impossible to have 2 electrons in the same orbital that have the same spin as each other. If there are 2 electrons in the orbital, they must have opposite spins, one up and one down. All right, so that's the Pauli exclusion principle. So when we start we're working towards learning how to put electrons into orbitals and figuring out in an atom how many electrons each orbital has. And the first rule we're going to follow is Pauli exclusion. We can never put more than 2 electrons into a single orbital. And if we do put 2 electrons, they have to have opposite spins. So that's a fairly important one. Now we can also think about some relationships now that involve the maximum number of electrons that we can have in a given shell or a given subshell. So we're going to arrange electrons into different orbitals within different shells and subshells. How many electrons can we possibly put into one of those shells? So as we already saw earlier today as a review, the number of orbitals in a shell is given by n squared. And as I just told you, because of Pauli exclusion principle, we have a maximum of 2 electrons per orbital, which means that the maximum number of electrons in a shell is equal to 2 times n squared. So if you have a maximum of n squared orbitals, you have a maximum of 2n squared as the number of electrons in that shell. Now that doesn't mean you will always have 2n squared, and that's just the most you can put in there at any given time, okay? And then the maximum number of electrons in a subshell, which would be, again, a pair of n sub n and l values together. We saw earlier that for a subshell, the number of orbitals is 2l plus 1. And because you can put at most 2 electrons in one orbital, that means the maximum number of electrons in a subshell is 2 times 2l plus 1. Or 4l plus 2 if you want to simplify it. Okay? So again, these are maximum numbers we're talking about here. This is not necessarily how many there are going to be, but this is the most you could put into a shell or a subshell. So when we start doing electron configurations where we're going to start figuring out specifically for subshells how many electrons are in each subshell, if you go beyond this number, that means you're violating Pauli exclusion principle and your arrangement can't be correct. So as some examples of how we apply these rules then, going back to the third shell that we've already talked about earlier in terms of orbitals. So the n equals 3 shell, the maximum number of electrons in n equals 3 is going to be 2 times n squared, which is 2 times 3 squared, or 18. So that means at most in an atom, the third shell, n equals 3, can have 18 electrons in it. Now, those 18 electrons are going to be in all the different orbitals. They can't all be in the same orbital, obviously, because there's only 2 electrons per orbital. So then if we look at the different subshells within n equals 3, so for n equals 3, we have the 3s, 3p, and 3d subshells. In 3s, the maximum number of electrons, because we're giving an L value here, is going to be 2 times 2l plus 1, which is 2. For 3p, the maximum number of electrons L equals 1 in this case, so it's going to be 2 times 2l plus 1 is 6. And then for 3d, I'll write it out in full so I don't confuse anybody. The maximum number of electrons for the 3d subshell, now L equals 2, so it's 2 times 2 plus 1, which is 10. All right, so what this means is that if we're going to put the maximum 18 electrons into the third shell, n equals 3, 2 of those are going to be 3s, 6 of those are going to be 3p, and 10 of those are going to be 3d for a total of 18. So that's how we're going to arrange them in the subshells. So the L value tells us how many at most we're going to have in each subshell within a given atomic shell. Now these numbers are going to also, as we'll see, be easily determined from the periodic table, so we don't have to even, especially this 2L plus 1, we don't even necessarily have to remember because the periodic table will give that information to us directly. But that is going to be sort of the maximum we can do for any subshell. All right? So then what we have to decide, knowing some of the rules, the last thing we need to figure out is, so, which subshells, how do we arrange the electrons into subshells? How do we decide, whether we put them into the first shell, second shell, third shell, whether it's the, which subshell within those shells? How do we decide how to arrange them? So now we know sort of some of the rules associated with arranging them, but how do we decide what order to put all the electrons in? And so for this, we have to think about what are the factors that determine the energy of the electron. Because as we're working towards, basically, we're going to fill the electrons from the lowest energy subshell to the highest energy subshell. So you always fill the lowest energy subshell first, and then we work our way up and up and up to higher energy. So we have to decide, how do we know which subshells come at lower energy versus higher energy? What are the factors that influence that? And again, this information comes from the periodic table, but we want to understand what is sort of the origin of this ordering of subshell energies that we're going to be dealing with as we move forward in this. So there are two factors that influence the energy of an electron in an atom. We already talked about this one to some extent in the context of the Bohr model, which is you have attractions between protons and electrons. That's what sort of binds the electron in the region of the nucleus and holds the whole atom together. And so basically what happens is that as you increase the charge, either in the nucleus or in the number of electrons, as you add more positive and negative charges, the attraction becomes stronger. So if we think about the nucleus then, the more protons that you have in the nucleus, is going to result in stronger attractions between the electrons and the protons, which then correlates with a lower or more negative energy. All right, because we're dealing with attractions here between opposite charges, so the energy is defined as negative, and the stronger that attraction, the more protons you have holding onto that electron, the lower the energy of the electron is going to be. All right? And again, from this comes from the Bohr equation, which has that z squared term in it that we don't really talk about for Bohr model too much. But the Bohr equation tells us, even though it's not valid for multi-electron atoms, that the more protons you have in the nucleus, the lower the energy of the electron. So that's one factor that influences the energy of an electron, is the attraction between the protons and the electrons. But then when you have multi-electron atoms, and this is the reason the Bohr equation doesn't work for multi-electron atoms, is you also have electron-electron repulsion, which is that the two or more electrons that you have are going to start repelling each other, and that's going to also influence their energy. All right? So in multi-electron atoms, the electrons experience repulsive interactions with each other. And those, because they're interactions between particles that have the same charge, negative charged electrons interacting with other negative charged electrons, that's going to raise the energy of the electrons. So when you're determining the energy of an electron in a multi-electron atom, which is what we need to be able to do to figure out how to arrange those electrons in different subshells, there's two competing factors. There's the attractions between the electrons and the protons in the nucleus, which sort of lowers the energy or is a negative contribution to the overall energy. And then there's the electron-electron interactions, which are repulsive interactions that sort of raise the energy. And it's those two things sort of competing with each other in some sense, a balancing act or a teeter-totter effect. And so what you want to be able to do to be able to minimize the energy of an electron in an atom is you want to maximize the attractions to the protons and you want to minimize the electron or electron repulsion. So it's sort of those two effects that are always going to compete with each other when you put electrons into different subshells. So what we have to understand then is the effects then within the different subshells that are going to determine these electron-electron and electron-proton interactions that are key for determining the energy. So there are two key concepts here. So the first one is shielding. And so when we have multi-electron atoms, we're going to have basically the phenomenon called shielding is going to reduce the nuclear charge experienced by the electron. And sort of a simple way to think about this is that electrons that are closer to the nucleus, so remember that not all subshells are going to be the same distance, not all orbitals are going to be the same distance from the nucleus. So electrons that are close to the nucleus are going to sort of block the outer electrons and partially cancel out the positive charge of the nucleus. Okay? So the inner electrons, the ones that are closest to the nucleus, are going to block outer electrons, and those outer electrons are going to be blocked from feeling the full nuclear charge. All right, so remember that we use the abbreviation Z for the number of protons in the nucleus, which would basically tell us what's the positive charge in the nucleus. And for outer electrons, we define, or for multi-electron atoms, we define what's called Z effective, ZEFF, which is going to be smaller than the actual nuclear charge Z for those outer electrons. So if we have, for example, a carbon atom with 6 protons in the nucleus, where Z equals 6, the electrons that are furthest away are going to be partially blocked by the electrons that are closer, and so their effective charge that they experience is going to be less than the full 6. So effective nuclear charge, Z effective, being smaller than the actual nuclear charge for the electrons that are furthest away from the nucleus. And then the other effect, which sort of dictates the ordering of subshells within a given shell, for example, 2s versus 2p, if n equals 2 and we have 2s and 2p orbitals, which ones are going to be lower in energy? And the key determinant for this is going to be what's called, the concept is called penetration. All right, so the penetration is the ability of an electron to get close to the nucleus. I can tell you guys are starting to zone out because you didn't giggle when I said that word. All right, thank you. I didn't want you to. That's the sign of maturity, which I appreciate. You apparently are more mature than I am. All right, so it's the ability of an orbital or an electron in an orbital to get close to the nucleus. And what it does is it reduces the effect of shielding. So if we want to maximize those attractive interactions between the protons and the electrons, the closer the electron can get to the nucleus, the better off it'll be, because the closer it is to the positive charge, the more it's going to feel those positive charges, the stronger it's going to be attracted. So if we look at 2s versus 2p, and think about their radial probabilities, again, 4 pi r squared psi squared, that radial probability density, and as a function of r distance from the nucleus. If we look at a 2s, remember that the 2s has a radial node, and it has this little region of probability that's close to the nucleus. All right? And then it's going to have the second peak out further away. All right, so that's our 2s. And then in red, I'll do the 2p orbital. Now, the 2p does not have a radial node. It just has a single maximum radius, and actually that maximum radius for 2p, as it turns out, is a little bit closer than 2s, so I'll try to indicate that here. It's a sort of a broader distribution, but it's a little bit closer on average than the 2s. But in the 2s orbital, we have, again, this little region here, relatively low probability, but a small probability of the electron getting really close to the nucleus. And that effect is called penetration, meaning that the 2s electrons are able to penetrate to the nucleus better than the 2p electrons. And so what that means is that the energy of the 2s orbitals is going to be lower than the energy of the 2p, because electrons in a 2s orbital are able to get closer to the nucleus, and they're going to experience a larger nuclear charge as a result. And so what that means is in any given shell with a certain quantum number n, the S subshell is going to be lower in energy than the P subshell, which is lower in energy than the D, lower energy than F. This is true if we're comparing subshells that all have the same n value. So if we're in the n equals 4 shell where we have all 4 of these subshells, 4s would be the lowest energy, then 4p, then 4d, then 4f. So we're deciding sort of the ordering of the subshells. This is how it's going to be for any given value of n, and that's because of this effect of penetration, where the s electrons are able to penetrate closer to the nucleus than p and d and f. Sorry, I wrote p twice. So it'd be d. Okay? Where are we now? All right, the last thing we'll stop before we go into how to do electron configurations is define a term called degenerate orbitals. So degenerate in this case does not mean in violation of the law. What it means is these are orbitals that have the same energy. Okay? So we now know how to define orbitals. We now know how to predict how many orbitals there will be in a given shell or subshell. But some of these are going to have the same energy as each other. You're not going to have a unique energy level for each individual orbital. You're going to have, in many cases, some orbitals that are at the same energy as each other. So the orbitals that are degenerate are fairly easy to identify. Those are going to be the orbitals that are in the same subshell. So any orbitals that have the same n and l values are going to be degenerate with each other. All right. The first place where you'll see this is in the 2p subshell. So in a 2p subshell, L equals 1. So you're going to have 2 times 1 plus 1, which is a total of 3 orbitals. And we drew those earlier today, px, py, and pz. And those 3 individual orbitals, px, py, and pz, as we designated them earlier, are going to all have the same energy. So they're not going to be any different from each other. Okay? So if they're in the same subshell and they have the same n and l values, the orbitals have the same energy as each other. All right, so again, the 3 p orbitals, 2, 1, minus 1 for those first 3 quantum numbers, 2, 1, 0, and 2, 1, plus 1. The value of m sub l is different for all of them, but that doesn't affect the energy at all. We said earlier briefly that the value of n sub l, this third quantum number here, only affects the energy in a magnetic field, which in normal situations we're not in a magnetic field. So in regular situations, all 3 of these are going to be at exactly the same energy. So when you're sort of ranking orbitals and subshells in terms of energy, the orbitals in a single subshell are all going to be the same as each other. So when we come back next time, we'll put the rest of this off all until next week. We're going to talk about, again, a little bit more of how to arrange these subshells in terms of their energy, and then how to figure out how many electrons goes into each of those subshells for different atoms in the periodic table.